So yeah, I had some issue with my speaker, not resolved. I set 10 minutes, so let's wait a couple more minutes here. So as I said last week, we have to do what we didn't do last week to this entire lab, and the document for lab 5 is on Blackboard. So lab 5 for you guys will be that part of lab 4 that we didn't do, plus lab 5, the actual lab 5. So there's some take-home stuff there which we'll talk about. First, I want to go through the theory, and then we can talk about some circuits. They're pretty simple circuits. All of the details are in that document, so should not be a problem. But yeah, this I'll say pay attention to what's happening to the circuits, otherwise it can be confusing, especially the calculations. So and you will be doing some calculations today. I'll give you like 5 minutes and you will calculate the resistance or whatever. So first of all, you need to open the document from the last lab where you had that part that we didn't do. So that is essentially lab 5 for you now. So that is part of lab 5. Let me share that. So you guys did, yeah, but not this. So yeah, we start from here. Yeah, there's some theory involved here, so we're going to talk about that. The galvanometer, it's one of the most basic instruments. So the ammeters and voltmeters you see were developed from the galvanometer, and that is what exactly we'll be trying to do today. We'll be constructing an ammeter and a voltmeter from a galvanometer. And what a galvanometer does is it gives you it tells you about the slight changes in currents that are happening. It has a magnetic coil in there, and it has a needle connected to it. So when you have an electric current, we know that when you have an electric current, there are magnetic effects. So the needle will be deflected when there's an electric current passing near or through the galvanometer. So that is what it basically is. Now, how do we turn it into ammeter voltmeter? First of all, we need to look at the half deflection method. Yeah, half deflection method. What is it we are doing? So first of all, for this, we need to know. Let me draw the circuit here, and you can. People in the waiting room. Okay. So I will stop sharing this, and you can have this file open on. All right. So. All right. So we have deflection method. And you can note this down. So, okay, we have this circuit as it is in your lab. I don't know that. Can you see it on the screen? I don't know what happened to the plot. Yeah, but this is supposed to be 1080. All right, this is the same circuit as in your lab manual. So okay, what's happening? So you have a current, we'll call it I naught, that is coming. And what happens when you have two branches? So here at this point, you have two branches now. So the current will divide between the branches. That is what happens with the electric current is the flow of electrons. So that flow gets divided between two different branches. And that happens with current. With voltage, it doesn't matter. So voltage is potential difference. So the difference potential between these points, it doesn't matter which way you go. You can go through the upper branch, you can go through the lower branch. It doesn't matter. The potential difference between these two points is always the same. It doesn't matter which branch, but current is divided between two branches. So if we call this current going through this branch I1, the current going to this branch now becomes I0 plus I1. Is that okay? The current is divided as I1 is I0 minus I1. And we'll just use Ohm's law here. So I can write, since you know that voltage is equal between these 2 points. So the voltage here will be in the upper bracket I1 in resistance of the galvanometer. So we have a galvanometer here, and the current going through is I1. That gives us the voltage. So Ohm's law should be equal to the voltage in this branch, which is equal to. So now the current in the lower branch is I0 minus I1, and the resistance is, well, this resistance R1. And that gives us I0 minus I1 over I1 R. Now, what we do in half deflection method, can everyone hear me properly? There's someone saying that there's some audio issue. Interesting. Yeah. Is the audio there? That's not good. Okay. Oh, good. Let me. Okay. Okay. Is it better now? So, is it? Yeah, sounds the same. Now, is it better? No? Still bad. I think that other one. No. No? Weird. I don't know what happened. Never happened before. Hello. Hello. I think we have to do this. Yeah, it's kind of muffled. I think I have to be louder. So I think that will be a lot of work if I do that. I have to open my account. Yeah, I don't think that will work. I'll try to be louder now. Okay. Right. So we have I naught. Yeah. So I naught minus I1 over I1 is equal to RG. RG is the resistance of the galvanometer. R1 is this resistance that we have in the lower branch. I naught minus I1 is the current going to the lower branch. I1 is the current going to the upper branch. So that is what we get here. Now, what we want in the half deflection method is we want to make this RG equal to R1. How do we do that? Well, if these two currents are equal, I naught minus I1 and I1, if they are equal, then RG will be equal to R1. Now, it means that the current going to this branch and this branch should be equal. When will that happen? When will the current between the two branches be divided equally? What is the condition for that? Huh? It pertains to the resistance. You have the RG here, the R1 here. What is the condition here? When does the current? So we know current is divided between different branches. When a wire branch or whatever. So if the resistance to both branches is equal, then you're gonna have the same current. So if we come all right, so if we somehow get I1 equal to half of I naught, I1 is the I naught is the total current, I1 is the current going to the upper branch. If this is just half, which means the rest of the half is going to the lower branch, so equal amount of current is going to both branches. It will mean that these two resistances are equal. So RG will be equal to R1. And because we will have a resistance box, so R1 will be a resistance box here. So we will know what resistance we have chosen. So we can find RG when it is equal to R1. So we can find the resistance of the galvanometer, which is what we need to make it into an ammeter or a voltmeter. So when I1 is equal to I naught over 2, then RG becomes equal to R1. This is what we want here. this is the half reflection method. Not too complicated. So what we're trying to do, actually, I'll go over all the theory first, and then we'll do the experiments. Right. So we, as you can see, if you look at your document, look at the table. That will be in the lab 4 document, last page, I think. So you can see we have to do 3 trials. That is because we want an average value, and then we, then we can, it reduces the error. So we're doing it 3 times. What we'll do is we'll look at the galvanometer and we'll do it at 80% deflection. So there should be an 80% deflection on the galvanometer when the switch is open. When a switch is open, nothing is going through the lower branch. So everything, it does have I naught. So first we're doing it at 80%, but when the switch is closed, now you have 2 branches, so the current will be divided, and then we want the galvanometer to be at half deflection, which means only half of the current is now flowing through the upper branch. So 80%, then which means it, when it's closed, it should be at 40%. Similarly, in the second trial, if we do it first at 50%, with the switch closed, it should be at 25%, and similarly 40 and 20 in the third trial. So that is what we will do. There are some other things you need here. We'll do when we do the experiment. But for the ammeter now, so this was the galvanometer, the half deflection method. Now we'll look at the ammeter portion. You cannot see that. Right. We have the ammeter. All right, I'll draw the circuit here. Probably the same as, yeah. So this is your ammeter. This will be the lab multimeter that we're using. And here you have the galvanometer. You'll have a rheostat, a variable resistance, so that you can protect equipment. It just stop. Okay. As we have all right, the concept here is again very similar to the previous one. You have I current flowing through the circuit, then you have 2 branches here again. Here is the main branch with the galvanometer, and this is a shunt wire. And the current flowing through the upper branch is IG, we'll call it IG, and the lower branch will be I minus IG. So how, and the resistance of the shunt wire is R sub S, resistance of the galvanometer, as we know, is R sub G. And we already know RG from part 1. So here, the resistance, so let's do ohms law first. So I minus IG in the lower branch in the shunt wire multiplied by the resistance of the shunt wire is equal to IG in the R. I think that is understandable. We did the same thing here in the first part of the. Now we have different circuits. So we have this, and we can find the resistance of the shunt wire. This equation. We know IG. IG will be calculated in part 1. if you look at the end of the table, it says maximum current IG for galvanometer. That will be calculated. So you have IG and RG from part one, one by RS. I here will be the full scale. It is whatever you want. So if you want your ammeter to be 500 milliamperes, you will put 500 milliamperes there. It doesn't matter what is on the galvanometer. The galvanometer might say the full scale reading is microamps, some microamps. You don't care because now you are choosing what you want the range of your galvanometer to be. So whatever you put in here, I becomes your range. That is how the galvanometer is going to behave. So we are manipulating it. And in this case, we are choosing, and I think it's also in the document, is 500 milliamperes. It will be 500 milliamperes. So ID and RG come from part one. We know I and RS can be calculated. And now you know RS. You already know that R is well. You know that. So, and here is given on the last page of lab 4. You'll see. You have to find the length of wire. You know the resistivity is given. It's copper, so the resistivity is given. The resistance is equal to this, and well, the cross section. I'll give you the diameter of the wire, and from there you can find the cross sectional area, and then you can find the length. So that is one calculation you have to do before we can move on. And after that, we'll just try to prove that our ammeter is working. So we'll have a lab ammeter. That is why we have this here. And the current is going through this, and the current will be also going through this. So we will just be proving that our ammeter works, and the values are actually close to the values, well, to the true value. And we'll see how much error we get. So after that, if you look at the tables in lab 5, so the first part says data table part 2, ammeter, and there we will look at the error. So this is the second part of the lab. Now voltmeter. If you have any questions, you can ask. These are simple concepts, but it can be easy to confuse here. All right, the third circuit also in your document is again we have a real stack. And here you should be careful from the language that is in your document. I think it's a bit confusing. But, we'll call this or not. Yeah, right. And you can see it. Oh, yeah, right. Now we're doing the voltmeter. Okay, we've done this. Now, as we know that the voltage across here and here, and if you go to this branch or this branch, doesn't matter. The voltage should be equal. So we're going to use that concept. And again, right, IG. And this is a voltmeter in parallel. Obviously, voltmeter needs to be in parallel. this galvanometer in this case is going to be acting as a voltmeter. So V, the voltage, should be equal to IV G. R naught is this resistance, RV is this resistance. It doesn't matter. The voltage, this voltage should be equal to this because voltage is not resistance. So we are using this concept. So R naught, this, and RV is ID is the current flowing through this branch. So this should be right now moving around, gives us yeah. So this is what it gives us. Total resistance here across this branch, if you call it just R, then we have to do RD. And while your final current and also in your lab manual, the last equation, the I is equal to just V over RD, which makes sense. It's just a current point. Doesn't matter. IG, we already have IG from part 1, RG from part 1. R naught will be again a resistance part, so we'll keep changing that. But V again is what you choose here. V is the range of the voltmeter that we want, and we will have it as 5 volts. So V will be choosing a range of the galvanometer of 5 volts. So this is what we're doing. 3 different setups. First, we'll find the maximum current and the resistance of the galvanometer, and then we're going to use those things to convert it into an ammeter and a voltmeter. Basically, the circuits you see here will be the circuit will be it's exactly the same connection. There's literally no difference. This and the first will do the half deflection method, and I have to set up here, so I'll have to move stuff now. I'll move my laptop, move my camera. Okay, the setup is here. Let me just make sure. Okay. There are some connections there. I think somebody removed all the connections, so let's do them quickly. Okay. Negative. This will be positive of R naught goes to the galvanometer. And this is a galvanometer if you don't know. And you can see that it has a range of 500 microamps. Doesn't matter what its range is. We're going to use it when we do it diameter and voltmeter part. We can change the range. We can manipulate that. So yeah, it goes to right, that's what the other decoding. Now we have R1. So the white resistance boxes are not the black resistance boxes are R1. We have the switch here, so switch open, switch closed. All right, Kelvin positive. Negative resistance goes to switch. I mean, a couple more. Okay. All right, so let's hope this works. Power supply on. Okay, we already have something here. I'm gonna make sure the resistance in both boxes is 0. You have to turn off everything. Fine. Right. So as you can see right now, on the galvanometer, the deflection is way past full deflection. First, we needed to get to full deflection. So we're gonna choose some resistance here on the well, R naught. Let's see. I think this is full deflection that we're getting. Yeah, so it's 2000 plus 200 plus 300 plus 400. It's 29 at 2900 ohms on R naught. We're getting a full scale deflection. Exactly, it's exactly at 500. Exactly full scale deflection, and use a digital multimeter precisely measure these curves of parameters on that here. So the value of R naught with S open, and as you can see, S is open here, is 2900 volts. Sorry, ohms. 2900 ohms. And you can note that down. That's in the table. Record the value of R naught with S open needed to get a full scale deflection of the galvanometer. That is 2900 ohms. Okay, so now we know that. Now we need to get it to, now we need to do the trials. So 80% deflection. So let's add some resistance here. Needed to get 400 because it's 5. So let's go again. 3, 4. 4 is not much. Yeah. The 80% deflection, it's at 400. It's at 400 exactly. When I have, so let's see what I have here. I have sorry, I'm not 3700, yes. 3, 300, 400. So 3700. At 3700 ohms. It's at 400 with S open. Actually, let's go to 2900 first because we are getting something. 29. So the full scale deflection, we need to measure the voltage at that. Yeah. All right, the voltage here is 1.582. The voltage here is 1.582 at full scale deflection with S open. 1.582. So you can note that down as well. Yeah, with S open, we can only measure R naught. There's no R1 if S is open. So, okay, now let's. Okay, S is open now. Let's go back to 2700. And now I'm gonna close the switch. Now we will measure the half scale deflection. So I need to change R1 so that we get a half scale. Now we should get, so 400 was 80%, so we should be getting 200 now. 200, exactly just 200 ohms. 200 ohms. Actually, make it 220 ohms. It was slightly off. It's a parallel actor. You have to see it from straight ahead. So yeah, 220 ohms in the first column when S is closed. All right, let's move on. S open again. Doesn't matter what's on R1. R1 is not in the circuit anymore. So switch open. Now we're gonna look for 50% deflection. So let's turn off everything here on the resistance box. 50. So it should be between 200 and 300. 4K. Okay. Yep. And I think this is perfect. This is exactly between 200 and 300. So this is 4 plus 2 plus 200 plus 100. So 6,300. Yeah, it's 6,300 ohms. 6,300 ohms for the second part. It's at 250. 6,300 for 250, which is 50% deflection. Now we want it to be at 125, half of that. When switch is closed, I'll close the switch and now change some stuff here. Let's see. Should be at 125, right? 125. This is 120. It's again 220. Again, the value of R1 when switch is closed is 220. So at 220 ohms for the value of R1 when the switch is closed, galvanometer reading is 125. Okay, that's done. Let's look at the final one, final trial, 40% deflection, switch open again. So it should be 40%, so 200, we want 200. It's exactly 8,000 ohms on R0. 8,000 ohms on R0. Yeah, that's what we're doing. Galvanometer reading when S is open. 80% since the full scale deflection on the galvanometer is 500 microamps. 80% of that means 400 microamps. 50% means 250 microamps, and so on. And on the S close, you want half of that. So when it's 400 with S open, it should be 200 with S close. When it's 250 with S open, it should be 125 with S close, and so on. And we are finding the resistances at which that happens, the value of R0, and more importantly, R1, because we know that when we have the half deflection, R1 becomes equal to the resistance of the galvanometer. This is basically, we're finding the resistance of the galvanometer here. All right, the final one is 200. So yeah, with S open, it is 8,000 ohms. So 200 microamps at 8,000 ohms. With S closed, let's close the switch. Now, it should go to 100. That's what we want. Half of 200 is 100. So 200 at R1 is 200 in the third row for the third trial at 40% deflection. 40% means 40% at S open. When the switch is closed, we just want half of that, which is 20% deflection, which is 100 microamps, and that happens at 200 ohms. Now, what you're going to do is internal resistance of galvanometer, which is the average value of R1. Since by using this method, we have made the resistance of the galvanometer equal to R1. So we got three values of R1 from those three different trials. You're going to take an average value. So the internal resistance of galvanometer is the average value of the three R1s. You got calculation of maximum current. So value of R0 at 100% deflection, which is what I told you in the beginning, and the power supply voltage that I calculated from the, I measured from the multimeter. So those two from there, just use Ohm's law, V is equal to IR, you can find the maximum current. Is that clear? How to find the maximum current, IG? Yes, R1 at 40% deflection is 200. And I think everyone, well, you're using the R, the value of R0 at 100% deflection. You want the maximum current, and that will be at maximum deflection. And maximum deflection, that is something I did at the beginning. So the value of R0 from there, not the R0 in the three trials, but the value of R0 at 100% deflection, and the power supply voltage at that deflection as well. And you can check with the multimeter. And I don't remember the voltage. What was the voltage? 1 point something. Yeah. So you use those two values at 100% deflection, not the ones that are in this table, but in the three trials. The two values that you're using are in the next row where it says voltmeter reading. Those two values are the ones that you'll use to find the maximum current for galvanometer. Does everyone understand how to find the maximum current? IG. I mean, I can do that again. I don't mind. I believe it was 2900 ohms. The value of R at 100% deflection, 2900. And again, this is my voltmeter to measure this. And it will give me the same thing. Which is 1.582. 1.582 volts. These are the two values that you will use: 2900 ohms, 1.5 volts, that you will enter here first in the table, and then you will find the maximum current using Ohm's law. And that's the first part. Now, you know the resistance of the galvanometer, you know the maximum current of the galvanometer, so you know RD and IG. So using those equations for part 2, ammeter, you will find the resistance. So for that, I, as I said before, is equal to 500 microamps. That's the range we are choosing, 500 microamps. On the galvanometer, it says, sorry, milliamps, 500 milliamps. The range we have chosen is 500 milliamps. On the galvanometer, it's microamps. We don't care. You can choose any range you want. It's 500 milliamps now, the total range. So that is I. And so find the resistance. Find the resistance of the shunt wire that we need. And from there, you probably need the diameter of the shunt wire. The diameter of the wire is 0.65 millimeters. 0.65 millimeters. And you can convert that to meters, and then you can find the the length of the shunt wire that is needed using the equations that we discussed before. I'll do the same here. You can do that as well. I'm waiting for you guys. I will not proceed until you guys tell me what length of the shunt wire. Uh, 65 millimeter, not 65 millimeter, 0.65 millimeter. 0.65. It's not 65 millimeter. That's 65 millimeter would be a very thick wire. So take like 5 minutes and do this. We did 3 trials because we wanted to get an average value. Yeah, because they're often that is correct. Just the R1. R1 is equal to RG at half diffraction. Yeah. Yeah, R0 was just because it was a By the way, guys, the shunt wire, it's a low resistance wire. So if you're getting low numbers, it's fine. Low resistance band. Shunt wire is used so that most of the current flows through it. So it will be low resistance, not in 1,000. Make sure that you're getting all your units right. So since the diameter is 0.65 mm, make sure you convert that correctly. The cross-sectional area is obviously pi r squared, or pi d squared over 4. What is this? The resistance value? For the shunt wire, the RS, nah, that's too high. Shunt wire is basically nothing. The resistance is very low. Make sure you get your units right. That the IG, remember the IG that we got will be in amperes, but the I was in milliamperes. That's 500 milliamperes. When calculating shunt resistance, well, shunt resistance, as if you look at the equation that I wrote earlier, that's actually you should probably note it down. I mean, I can show it to you. Um, here, no, no. It's resistance of shunt wire is equal to Ig over I minus Ig uh, into Rg. Rg is the resistance of the galvanometer that we found in part 1 by basically equating that to R1. R1 is equal to Rg. That is the value that you will use. R naught doesn't matter. Or it matters when you calculate Ig, but not for Rg. Rg is just equal to R1. It's the average value of the 3 R1s that we found. And since they're all 3 of them are similar, it means that we did the experiment right. We got similar values of R1. All right, I have the value. You guys can take some more time, but once you get it, let me know. Yeah, I think that length that you got, Logan, I think that is correct. Thank you guys. I'll in a couple of minutes. Yes, you can be here once you finish this. I'm expecting it to do the other two parts like in 15 minutes. They're not that hard. And then after that, I can talk about the circuit, the document that you have to do at home, but they're pretty easy. The instructions are good. I think it'll be fun. So I'll talk about the 5 minutes. Yeah, let me set up the second circuit. You guys just use the that next. Okay. Now, tell me what length did you get? Thing is, you need to have that calculation in your lab report. You need to have that because I already know it. Already have the wire for it. So fine. Now I use the maximum term to yeah. So you guys need to have that in your lab approach, and that will be a considerable amount. And now let's look at this. Let's look at this setup. Let's remove clutter. What do we have? We have the second setup here. Okay, you have the rheostat. You can see that this thing is your rheostat, and this is the multimeter, which is the ammeter, and this is the galvanometer, which is also acting as the ammeter. So we have this setup. We have a shunt wire, which is connected across, is connected in parallel to the galvanometer. As you can see, the shunt wire is connected here, and the length of it you do not. Well, you must have calculated. If you don't, if you haven't, you have to. And now we'll see if it actually works. So the lab multimeter and this galvanometer should give us the same reading, same measurement of current. So I think in your lab manual, what these values we have to look at. Sometimes it can be hard to get that exact value, but the 0.1 amperes. Remember the full scale reflection on this galvanometer is now 500 milliamps, which is 0.5 amps. So we are looking at 0.1, 3, and 4. So on this galvanometer here, if you see, it obviously says microamps, but it's not microamps. It's now 500 milliamps. So those readings, 100, 200, they're all milliamps now. Because that's what we chose. That's what we put in the equation. Okay. So right now I have connected it, and on the, let me try and show it. Get to fluctuating between 0.09 to 0.1 amperes, which is 100. So you can see here, it says 0.1, 0.1 amperes. And here on the multimeter, it's at 100, which means it's correct. It's exactly at 100. And that one is fluctuating between 0.1, 0.09, 0.1. So 0.1 and the power 0.1 amperes. That's the first one. That's increased current. Now the second one, 0.3. So now the actual current is 0.3, as it can be seen here. And on the lab, this galvanometer, it says, well, it's not exactly 300 milliamps. It's, okay, that's 280 milliamps, 0.28, 0.28 ampere. Okay, let's try the last one at 0.4. At 0.4, now 0.4, and here it is as you can see, it's again not exactly 400 milliamps. It's again 0.38 amperes, 380 milliamps, or 0.38 amperes. Then you can calculate the percentage error. Percentage error is the theoretical minus experimental value over the theoretical value. And it's always positive. The error percentage is always positive. It cannot be negative. Did everyone get that? Okay. So this one was simple. We have all the data that we needed, and we just confirmed that our animation works. But make sure you get that length of the wire. Okay, I'll turn this off now. Make sure the next setup is working. Take it up. Remember the desired full scale reading for the voltmeter. So if you look at that, those things, make sure you get all these details in that. reading that in lab 5 document is 5 volts. That's what you want. We're choosing 5 volts. Uh, all right. The power supply you can see in the back. Then you have again the rheostat. If you look at the circuit diagram, it's exactly like that. So the rheostat after the battery, then you have the voltmeter right here, and then you have the galvanometer, and you have the resistance box. So same setup, connected exactly like in the circuit. It's everything's in parallel here. You can see that you have power supply is connected to the rheostat then connected to the voltmeter connected to these two, which are in series together. Okay, first of all, desired full-scale reading is 5 volts. 5 volts. That is our full-scale reading. Now, now when I have 5 volts coming in, these 5 volts. So this is the closest I can get. 4.98, 5 volts. So you can see 5 volts here. Well, 4.98, 4.97, whatever. Now I need to see at what series resistance. So there is a series resistance, a resistance box. At what resistance do we have full scale deflection? Right now, as you can see here, we are way past the full deflection. We need to be at full deflection here. So let's choose a resistance that gives us that. So 1, 2, 3, 4, 9,290. Yeah, 9,200 ohms. At 9,200 ohms, series resistance 9200 ohms. We have a full scale deflection. That's 9,200. Now, RG, we already know that from part 1, the average that we got, the resistance of the galvanometer. Yeah, it's as you can see, it's basically 4.98, whatever. Digital multimeter voltage. R naught for full scale deflection is again the same thing as before. It's 9,200 ohms. And then Imax is the current required for full scale deflection at desired voltage is above. So you can calculate I is equal to V, which is 5 volts, over RG and R naught, which we now know. Yeah, it's 9,200, 9,200, 9,200. Ohms, by the way. Right. So now we have this. Let's see if it works. We need to look at 1, 3, and 4 volts. So change, get as close as possible to 1 volt. It's exactly at 1 volt. That's 1 volt, as you can see on the multimeter. What is the galvanometer reading? Exactly 1 volt. Remember, the full scale reading is now 5 volts. So those numbers don't mean anything. 100, 200 microamp, those don't mean anything. The full scale deflection is 5 volts, which means this 100 right now where it's at is 1 volt. So it's at 1 volt exactly, yeah, at exactly 1 volt, which means it's working now. Yeah, series resistance required and R not, they're the same. Okay, let's try three. Let's have 3 volts. I'm at 3.01 on the multimeter. So 3.01 on the multimeter, which is pretty close. And here on the galvanometer, we have it's slightly more than we just a little bit. You can say it's three. It's almost 3.01. Yeah, you can say it's 3 volts. Yeah, it's 3 volts. It's slightly more. So it's closer to 3.05. Yeah, right, 3.05. 3.05 for the galvanometer reader. 3.05 at 3. And final one, 4. So at 4, it's again exactly 4. 4 volts at 4 volts. And yeah, you can find error where there's no error, you just write 0%. Right, and then you probably have some, it says make some circuits, answer some questions, and that is everything is based on the concept of visual circuits. And you can look at the equations again, which you'll need for the questions at the end for this lab. So yeah, 90 to 100. That's R naught in the third part. Oh, okay, long lab. 90 to 100 is the R naught, the series resistance required. You have to enter it 2 times for some reason in that in your document. I don't know why. Okay, let's share that document. What else is there? The results for what result? 1 volt. I think it was just one, if I remember correctly. The only difference was with 3 volts where we got something like 3.05 volts, but everything else was exactly the same. All right, so this is the lab. We have done this part, so this is done. Here. Yeah, your circuit, your homemade voltmeter, blah blah. Questions, we'll answer. Post lab questions. You'll do that. The first part though, you have to create this circuit. Now, hopefully, you all have you all the circuit in lecture courses. This won't be as hard. Now, you can see it's two resistors in parallel, another one in series with those. So you have to do this. Hopefully, you are comfortable with doing that on your breadboard. Using a 3 volt battery, measure the current at point A. So I think this should be pretty simple for you as long as you have capacitors and you know how to do it. If you haven't been able to do it, you can do it in the lab, but you should be able to do it now. Measure voltage at different resistors and calculate those voltages. Measured voltage, calculated voltage. You know what the voltage should be. You know how to calculate the resistances. Then you can, using just Ohm's law, you can calculate the voltages. So yeah, measure total resistance, calculate total resistance, and then calculated always means theoretical, by the way. Again, this circuit, now you have 4 resistors. And first, you have to figure this out. Sometimes these can be more complicated. These can look more complicated than they actually are. So you have to first simplify these circuits, look what's actually in series and what's actually in parallel. So yeah, these two are in parallel. This is in parallel. This one. This should be doable. Yeah. Okay. Yeah. So you have to create this circuit and do the same thing again. Measure voltage, calculate voltage, and write the percentage difference. So this is the take-home activity. Just want to make sure that you are comfortable with creating circuits. So these are 2 circuits that you have to create. If you have any issues, no. And the next part is about an LED. So obviously, if you use an LED, you need to make sure that not much current is passing through it because it requires very small current. If you have more current than required, then it can easily destroy the LED. You have to in this lesson, you'll learn how to change the brightness of an LED using different values of resistors. Yeah, if you don't use the rest of the LED, it may well be destroyed. So resistors help stop flow of current. All right, you have to create this circuit, and you need this thing. Was this in the lab equipment, that document? Should have been. Okay, then it's fine. And you already have it. The exact circuit is given to you, so I don't know. I mean, shouldn't have any issues there because literally the circuit is given to you how to create it on the breadboard. The convenience source of 5 volts used for the LED and the resistor. You don't need to do anything with it except to plug it into the cable. Is it 220 ohm resistor? Is it bright? Then you put a 1000 ohm resistor, then a 10,000 ohm resistor, and then you just keep checking is it bright or not. And then it says for the red jumper lead out, breadboard touches the hole and move it so that it acts like a switch. You should be able to notice it. This is a experimental stuff. They're asking what happens when you use this and that. There's not much to talk about, so you'll just write your observations here. if you have done the circuit properly, then there shouldn't be a problem, and the circuit is given here. Extra points. Create a circuit with RGB LED. Okay, three colors. So this is extra points. Again, we'll have it for 10 extra points for anyone who does it. Don't forget to set up. So yeah, this is extra points, and then we've already done this one. So it's just creating some more complicated circuits now, and yeah, that's it. Are there any questions? Questions? You probably have. Okay, some. Yeah, it's still a lab 5. You don't have to put it in lab 4. You can just put it in lab 5. It's basically lab 5 now. Lab 5 is these 3 circuits that you have to do with the extra points. So make it 4, and then what we did today, that is lab 5 now. So yeah, some take-home part, but the experiment part is done. You just have to do some calculations, have to answer some questions. If it takes more time, let me know. If it's taking more time for you to understand everything and answer the questions, let me know. But I think 1 week is still enough to do all this. And you probably will have some more questions. Again, let me know if that happens. Okay. So yeah, that's your lab 5. What we could have done is done the half deflection method last week, then just ask you to calculate the resistance and the length of the wire. That could have been possible, but yeah, it's better to do it one day because the concepts are very similar, and it's just the reason we do the half deflection method is because we want to convert it and just do it in all one day. It's difficult for students to do it in one day because they're doing it for the first time, but for me and because you guys are just watching. Okay. So yeah, that's it for this lab. If you guys don't have any questions, then yeah, that's it. Have a good week. I'll see you. Yes, and now people who are waiting can come into the lab. Otherwise, yeah, you're free to leave.